The separations of ethyne-ethene mixtures is of industrial importance because ethene feedstocks to polymerization reactors need to contain less than 40 ppm of ethyne in order to prevent poisoning of the polymerization catalyst. Typical compositions of ethine mixtures that need to be separated are 1 portion of ethyne to 99 portions of ethene. And today I'm going to discuss how we go about selecting MOFs for ethyne-ethene separations. Let's consider experimental data on breakthroughs of 199 ethyne-ethene mixtures at a total pressure of 100 kilopascals and at a temperature of 298 Kelvin, published in Nature Communications in 2020 for 2 different MOFs, ZUL-100, shown by the red circles, and ZUL-200, shown by the blue triangles. The experiments were carried out in the same breakthrough apparatus with an pack length of 0.05 meters. The mass of adsorbent MOF in the tubes are not the same. For ZUL-100, the tubes were packed with 0.3125 grams of the metal organic framework. For ZUL-200, larger mass of adsorbent, 0.6873 grams, were used in the breakthrough experiments. The flow rates of the gas mixtures entering the fixed bed tube is the same in both cases and is 1.25 milliliters per minute. These are the breakthrough curves in which the dimensionless concentrations at the exit are plotted against the time expressed in minutes. In order to compare these breakthroughs in a fair manner, it is necessary to use a modified time parameter in which we use the parameter Q0, which is the flow rate of the gas mixture at the inlet in the units of, say, liters per second, multiplied by the time in units of, say, seconds, divided by the mass of adsorbent expressed in, say, grams. So the units used for the x-axis is liters at standard temperature and pressure conditions per gram. This is a kind of a corrected or modified time parameter that takes account in a proper manner of differences in flow rates and masses of adsorbents used in the experiments with the different MOFs. Using this as a modified time parameter, we note that the time interval during which purified ethene may be recovered is longer with ZUL-100, indicated by the red arrow, than that indicated by the blue arrow for ZUL-200. The productivities of purified ethene conforming to the requirement of less than 40 ppm ethine may be determined from numerical analysis of the breakthrough experimental data, and the productivities of purified ethene are respectively 134 moles per kilogram for ZUL-100 compared to 106 for ZUL-200. So we can screen MOFs and evaluate MOFs by comparing the breakthrough experiments using the modified time parameter as shown on this graph. Now I ask the question, is it possible to obtain a reasonably good and fair ranking of the MOFs not by using breakthrough experiments, but by using the ideal adsorbed solution theory for description of mixture adsorption equilibrium? The simplest way to model transient breakthroughs in fixed bed adsorbers is to adopt the shockwave model, in which the concentration of ethyne and ethene are assumed to traverse the length of the fixed bed in the form of shock waves, and this leads to a breakthrough curve that has the characteristics as portrayed here by the continuous solid green lines. The details of the shockwave model are described in my papers that are listed here. Watch also my videos on transient breakthrough simulations and screening of MOFs for mixture separations on my YouTube channel. Based on the shockwave model, we can determine the productivity of purified ethene in the form of this expression for a parameter called delta Q that has been dubbed the separation potential. Delta Q equals Q1, which is the molar loading of component 1 in the adsorbed phase, that is in equilibrium with the mixture of ethyne and ethene with mole fractions Y10 and Y20 in the feed mixture. Q2 is the molar loading in the units of moles per kilogram of component 2, which is ethene. Q1 and Q2 may be determined from the ideal adsorbed solution theory of Myers and Prausnitz. So adopting the shockwave model, we can determine the separation potential, and this separation potential indicates the maximum productivity that is achievable for binary mixture separations in a fixed bed adsorber. For 199 ethyne ethene mixtures for ZUL-100, the value of delta Q is 200 moles per kilogram, and from the breakthrough experiments, the productivity of purified ethene is significantly lower, and it amounts to 134 moles per kilogram. The reason the productivity is lower is because of diffusional limitations. The breakthroughs obtained in actual practice have a more distended character than the breakthroughs that result from the shockwave model. An important advantage of defining the separation potential is that this parameter delta Q may be used for a ranking of MOFs using the ideal adsorbed solution theory for calculations of delta Q. In this graph, I plot the separation potential delta Q, and on the y-axis, I plot the ethene productivity from the experiments for ZUL-200 and ZUL-100. In most of the examples I've encountered, the actual productivity from experiments is nearly linearly related to the values of the separation potential that is determinable using the IAST. So the message to emerge from these discussions is, firstly, when comparing breakthrough experiments, we need to use a modified time parameter, as explained in the earlier slide. And for ranking MOFs, we can use experimental breakthroughs, of course, but we may also rank and evaluate MOFs using the separation potential calculations from use of the IAST. Let's now proceed and examine separations of mixtures of propyne and propene. Propene feedstocks to polymerization reactors should also contain less than about 40 ppm of propyne in order to prevent poisoning of the polymerization catalyst. So let's examine the selection and evaluation of MOFs for propyne-propene separations. We first examine experimental breakthroughs for 199 mixtures of propyne and propene using SIFSIX copper TPA, as reported in this paper published in Chemical Science in 2023. The experimental data are shown by these red circles here, and the productivity of purified propene can be determined from numerical analysis of the breakthrough experiments, and the productivity of purified propene is 50 moles per kilogram. If we adopt the shockwave model for describing the breakthroughs, we can determine the maximum productivity that is achievable in a fixed bed adsorber, and the expression for the maximum productivity is given by delta Q. Q1 and Q2 are the molar loadings in the adsorb phase in equilibrium with the bulk gas phase feed mixture with mole fractions Y10 and Y20 of propyne and propene. So this is 0.01 and Y20 is 0.99 for 199 mixtures. The value of delta Q using the IAST works out to be 74 moles per kilogram. That is higher by about 50% than the value of 50 moles per kilogram obtained from the experimental breakthroughs. The experimental breakthroughs lead to lower productivity because of the distended nature of the breakthroughs caused by, say, diffusional limitations within the adsorbent pores. So the MOFs for propane-propene separations can be screened and evaluated by examining experimental breakthroughs. Alternatively, they may also be ranked on the basis of the separation potential. These two procedures are interlinked, as we shall see in the following slide. In this graph, I compare the experimental breakthroughs of SIF6 copper TPA, shown by the red circles, with those obtained for 199 propane-propene mixtures with an ultra microporous MOF with a square lattice that is reported in this paper, the Journal of American Chemical Society, in 2023. The experimental breakthroughs are reported by two different groups with two different breakthrough apparatus, and for a fair comparison, we use a modified time parameter as described earlier, and this modified time parameter is the flow rate of the gas mixture at the inlet, Q0, times the time in say seconds divided by the mass of adsorbent, and in this case the units of the x-axis used is liters per gram. On this basis, we note that during the interval shown by the green arrow, purified propene can be recovered with the ultra microporous MOF with a square lattice structure shown by these green symbols. The productivity can be determined from the breakthrough experiments, and it's determined to be 118 moles per kilogram, the highest value recorded for 199 propane-propene mixtures. This value is more than factor 2 higher than the productivity of propene that is achievable from SIFSIX copper TPA, which is 50 moles per kilogram. I plot here on the y-axis the experimentally determined productivity from these two breakthrough experiments as a function of the separation potential for these two MOFs that is determinable from the IAST, and we note that the experimental productivities are linearly related to the delta Q values determined from IAST. So the message is reinforced that the screening of MOFs for alkyne-alkene separations can be based on experimental breakthroughs using a modified time parameter or on the basis of the separation potential calculations determined using the ideal adsorbed solution theory of Myers and Prausnitz.